Hi everyone! In this new episode, I would like to reconsider Voronoi generation in WebGPU, but this time from a procedural texture generation perspective, as opposed to the original technique I mentioned in a previous recording, where I was rendering actual polygons and lines and running a full Delaunay triangulation on every frame actually. So here is a small overview of the final result that we will achieve in this tutorial. We will see how to display different colors for the different cells, how to display a small circular dot at the center of each cell, and how to also apply this time animation on the full Voronoi diagram to get this constantly moving effect. We will also see actually how to change the grid size, for instance here, changing the size of the cells. But of course, before that, we will need to also cover some simple theory and preliminary computation steps to really understand how this algorithm works. Now, before we dive deeper, I have to mention here that I will roughly be following the same logic as in this ShaderToy example by Inigo Quilez. But, well, understanding the base code might not be so easy if you're not familiar with the algorithm yet, so we'll be providing some explanation in the process. Anyway, if you don't know Inigo Quilez yet, I would also highly suggest you pay a visit to his website and try to read as much as possible from there, especially the technical articles, because, well, honestly, this guy is a genius. And yeah, actually, I will make sure to also add a link to this page in the video description. And finally, just like the last time, I have added a dedicated folder in the Nerveland Adventure GitHub repository for this tutorial, where you will find the incremental versions of the compute shader we will create here, in case you would like to have a more careful look at this. So I will also add a link to this repository in the video description. And now let's get started. The first thing we need to do for this project is to set up a simple surface on which we will render our generated texture. As before, I will be using a minimal scene construction inside the Terrain View app as our playground. And here is the YAML element I use for this. The compute surface blueprint is a new type of element I just introduced, which can be used to specify an arbitrary compute shader that will generate a texture to display on the surface quad. In this case, for instance, we will use a shader from the file texture/Voronoi.wgsl, which we will get to in just a moment. Since we are generating this texture from scratches, note that we also have to provide the texture width and height that we should be using. And those texture dimensions actually have nothing to do with the dimension that we'll be using for the rendering of the quad itself. In the compute surface blueprint class, we then proceed in a similar way to what was done in the video surface blueprint described in our previous video tutorial. We will be allocating a dedicated area on our texture atlas to all the resulting texture data, and then we will set up some kind of processing to write valid data in that area. And this content will be shown on the final quad with the same mechanism as in the previous recording. So first we allocate the area with the appropriate size in our main texture atlas with this code. Then we create a compute node with the provided shader, and we set up the only binding group we will need for this shader execution. Of course, the code here is in the Nerveland engine, so it's not using pure native WebGPU API, But anyway, I think you should be able to grasp the main ideas. The param struct is used to provide a uniform structure on the shader side, as we need to provide it with the size of the texture that we want to generate and the origin point in the texture atlas where we should start writing the output data. And next, to build the bind group, we provide those params as what I call uniform buffer object in the engine. And we also provide the underlying texture coming from the texture atlas as a storage texture to the array, which is also writable by default. After this, we need to prepare the actual dispatch for the compute node and the binding group we just created. You see that here we use the texture dimensions to compute the dispatch sizes, and we assume that the workgroup size will be 16 by 16 by 1 in the shader. And finally, we add this compute node to the pre-render compute path that I have in the engine, which is a specific compute path executed once at the beginning of each render cycle and in fact before any other rendering step. Now let's take a look at the initial version of the Voronoi shader. First, we describe the inputs that we will be using in this shader. As mentioned before, we have a uniform struct called params, providing the texture size and destination origin point. And as a second binding, we have the output texture to the array, which is a full texture atlas, and we should write our computation results into a subregion of that texture. Next, I started with that version of the main function. As mentioned already, we have a workgroup size fixed to 16 by 16, and first we start with checking the texture bounds here, which is in fact very important because since we are rendering in a texture atlas, we may have some valid content outside of those bounds, so we don't want to overwrite anything outside of the subregion where we're supposed to render the image. And for now, we are simply writing a uniform yellow color for all the pixels. If we run the TerrainView app with this scene setup, we get this initial result, which is in fact exactly what we would be expecting. Next, we can, for instance, simply change the color from yellow to red and save the file. And when we do that, we immediately get the quad display updated to red, which means the compute shader is indeed working properly and the live reload feature is also functional. As a final test, we can, for instance, change the opacity of the pixel to 50% and save the file again. And this is the result that we will get after this change. So it also seems to work just fine. Even if, well, in fact, there are some artifacts due to the interaction with the Ocean post-processing shader, but that's something I will fix later on, so no worries about that. So this concludes the initial setup for the render surface that we did for our experiment, and now we can focus on the Voronoi generation process itself. Yet, before we really get started, we need a little bit of theory on how we will proceed here. The basic idea when generating Voronoi cells is that for each pixel or location that we have in a 2D area, we're considering, for instance, here this blue square, we will need to find the closest reference point to that pixel. And the reference point are those red dots on the image here. And then when we have that, we can declare that the pixel that we're considering belongs to the cell of that specific reference point, which is in fact also the center of that cell. And then maybe we can give it a specific color for the cell and also store the distance to the cell center to do some additional processing afterwards. Generally, we are given a set of random reference points that can move anywhere, and thus it's pretty tricky to follow them all, and for each update cycle and each pixel, you would need to reconsider all of them to find the closest. Yet, we actually have a way to simplify a bit this problem, and this is what we will see now. First, we will create a grid on top of all the pixels that we want to consider. So the pixels are this blue area here. And then for each of the grid cell, we will generate a single reference point at a random location, but inside the specific grid cell. After that, whenever we consider a given pixel, the problem of finding the closest reference points is simplified. We only need to consider the reference points from the cell containing the pixel and all the direct cell neighbors. So that's only 9 reference points to check per pixel. Now let's see how we could apply that in our code. First, we can compute the normalized UV coordinate of our texture as this, and we can display those coordinates. And that will give us a simple quad looking like this, which is exactly what we could expect. The origin of the texture is at the bottom left corner, and when we increment the U coordinate, or the x-axis here, we get more and more red, and if you increment instead the v coordinate, so the vertical axis, you get more and more green, and when you have both of them set to 1, you get to the yellow color here. But in fact, if we want to keep the grid cell square, it's easier to work directly with the texture size in pixel and think in terms of a number of pixels per grid cell. So we can rather use this kind of code. First, we will set a fixed value for the grid size here, and then we will be dividing the coordinate, the pixel coordinate, by this grid size to figure out what are our grid coordinates. If we take the integer part of those grid coordinates, we get the cell coordinates. So cell coordinate will be integer numbers, and if instead we also consider the fractional part of those grid coordinates, we get the local coordinate of our pixel into its own cell. So if we try to plot, for instance, those local coordinates, we will see values going from 0 to 1 on every single grid cell. So this will give us this kind of result. But from there I started to think it would be very cool to be able to manipulate this grid size parameter dynamically when building the shader. So why not try to add a dedicated control panel for it? To introduce this dynamic control support, I first added the possibility to configure and share some WebGPU buffers from my scene configuration file. Here, for instance, I'm defining a buffer called buffer0, and in this buffer we will have the texture size of the vec3 U, the grid size will be a float, and then the origin point will be another vec3 U. Then in the compute surface blueprint, I had to make sure that I would be retrieving this buffer that I'm describing in the config, and I would then update the parameters directly into this buffer instead of creating a new one that would be then provided in the binding group. So in the binding group, I'm also not providing this params buffer anymore, but instead referencing this shared structured buffer. Next, in the shader, I had to update the compute param structure to also provide the grid size. And finally, in the main function, we can now just use that parameter instead of the hard-coded value. With this first part of the update, if I change the default value for the grid size element to 256, for instance, in the config file, I get this reflected into the shader as expected on the next dot. After adding the support for the structure buffers definition in the config, I then further extended the configuration to also support the description of a control panel, as you can see here. In this element, we specify the control panel blueprint type, and then we can build a panel with a quite natural flow. We will be indicating the icon that should be used for the visibility toggling button that we have for this panel. Then we provide the title to show on the panel, and then we have a list of elements to display on that panel. For now, we only have one element, which is a slider row type, allowing us to modify the value of the grid size element from the buffer0 that we created before. With this new component, when I run the application, I can now dynamically control the grid size value, and the changes are immediately reflected in the shader and the display. So that's pretty cool. And you can go with very small size like this, but yeah, that's probably not what we're going to use later on. Okay, now before moving to the generation of the reference points, I think we need to improve a bit on the default display we have. Because, well, displaying the local UV coordinates is a bit confusing, and instead I would like to display a simple white background for each cell with black borders around them. So let's try to implement that. First, I had a new entry in the buffer0 config to control the border size. Next, I had another element in the Voronoi settings panel to control this border size directly on the control panel. Then I updated the compute param structure accordingly in the shader to also provide this border size parameter. And finally, we can use this new parameter to draw black borders on a white background when the provided value is not 0. Not that I'm using this check against 0 just to keep the possibility to display the UV coordinates, but you don't really need that. With those changes, here are the results that we get. If we increase the border size to a value which is not 0, we'll get the white background and the black borders. And you can change the size of the borders to make them as visible as you would like. So this will definitely help us to more clearly see where are the grid cells. And now, as promised, it's finally time to generate the reference points for each cell. We will need one pseudo-random but fixed location in each grid cell, which can easily be achieved using a hash function applied, for instance, on the coordinate of the bottom left corner of the grid cell. And personally, I was using this hash function so far already in my code to generate some noisy value from a given 3D integer input. And extending that a bit, here is the version that Claude AI came up with for our 2D needs. So you see that here the logic is pretty simple. We're going to do the same thing as for the 1D noise computation, but 2 times with different values. So we have the N1 and state 1 and N2 and state 2. And next, we can make use of this hash function to compute the reference point location into the grid as normalized coordinates, so in the range 0, 1. Just to give it a quick check, we will add some debug code like this to display those reference points in our grid. So we have a radius for those points, and we can kind of figure out if the current pixel is close to the location of that point, and in that case we will use a red color to display the point instead of the default white background color. If we run the application with this code now, this is the kind of result that we get. So yeah, we can finally display the red point, and you can see that if we increase the border size, and we get the white background instead of the UV display. And yeah, we can increase the size of those dots now. And in fact, I also added the control to change the size. But you can see that some of the dots were also clipped at the border of each cell. But this is expected with this simple debug display, given the fact that when you're crossing a border, then you're actually changing the location of your reference point. Now we need to find the closest reference point for any given pixel using the closest 9 cells around our current location as explained previously. So as in the base ShaderToy example, we will refactor our code to have a dedicated function to find this. This function is a bit long because I added some commands in the code, but the underlying logic is pretty simple in the end. So we start with preparing a ref point info structure with a very large distance to ensure that when we iterate on the different cells, we will definitely find a better solution. Then we split the grid coordinate into the cells coordinate part and the local coordinates. After that, we start iterating on each sibling cell, and we will start with getting the coordinate of the reference point, also ensuring that we convert that into the same frame as the current local coordinate that we have for our pixel. And then we'll use that location to compute the squared distance between that reference point and our current grid coordinate. And we may update the best solution that we found so far if this is applicable. Finally, we make sure that the distance value that we have in the result structure is indeed a distance and not the squared distance value, so we take the square root and we just return that result. Next, in our main function, we can make use of this function to figure out what is the closest reference point and assign a dedicated color to the pixel that will be related to the location of that reference point. So we'll be retrieving this grid position of the reference point and extracting some kind of random value from it, and we'll use this hash-free function to generate a color. This additional helper function is another kind of hashing function which is simpler than the previous one. So we're just using some sinus computation here to produce a random vec3. This is certainly not as good as the PCG hash function we used before, but it will do the job for the color. And in fact, we could just stop here with this RGB color value, and that would already display some unique color per cell and make a proper looking Voronoi diagram. But just like in the initial example from Inigo Quilez, we can also apply a simple darkening radial gradient to get some kind of non-flag effect for each cell. So this is what we do with this line, considering the distance that we have from the cell center to apply a darkening factor. And similarly, it's also very easy to display the cell center as black dots. We just use this smooth tap on the distance, and if we are below 0.08, then we're going to use a multiplication by 0, so RGB will become completely black. And with those changes, here are the kind of result that we can get. As you can see, we're already displaying a proper looking Voronoi diagram. So we have different colors, we have the cell center display as black dot, and yeah, it looks pretty nice. We can change the grid size, and the only really missing part now is that everything is pretty static, so it would be nice if we could add some time animation on top of this. So now let's get to this and see how we can add the time animation part. First, I add access to my camera specific uniform buffer when building the compute node in the compute surface blueprint, as this will give me a time value that I need. For reference, here is the content that I have for the STD camera uniform buffer object structure. And we are mainly interested in the last member here, which is the time value in seconds, I think. So then we have to reflect the changes that we just made, also providing the milding for this new structure element. And finally, we just use this time parameter to compute a dynamic move reference coordinate vec2. So this will be the previous static version that we were using, and now we're computing this dynamic version here. And here you see that we're simply using a sinus function with this time value and making use of the static location of the reference point to get some different location. And since we multiply that by 0.5 and add 0.5, this result here is still in the range 0,1, so it means we can still make use of this as the local coordinate, and it will be again in the given grid cell. And here we are. With this simple time parameter addition, we now get our Voronoi diagram to animate and change continuously as shown at the beginning of the recording. So mission completed. Now, this animation mechanism is not really perfect. If you pay close attention to the movements, let's say for instance we just look at this brown cell and the blue cells and those three dots, you see that every say 5 seconds they're going to come back exactly the same location, and so the movement is going to be repeated. So the cells themselves are going to be the same and they will be repeated continuously. In many cases, I don't think this would really be a problem, because if you want the animation and you get this kind of changes, that's probably good enough. But, well, Actually, that would be anyway different ways you could use to improve on this. First, we could use a more complex animation function instead of simply sinus of time plus a fixed offset. Or I was also thinking, more interestingly, you could maybe try to generate 2 or more reference points per cell. That would give you more random elements to experiment with. Or even better, you could consider using 2 or even more grids themselves. So that would be, you would have one fixed grid, for instance, the one we've been using so far, and you could imagine that there's another grid which is behind or above it, not even the same size for the grid cells, and that second grid could be moving compared to the first one. So that would give you 9 close reference points and 9 other bigger reference point to consider, for instance, which would definitely produce more random visuals here. But anyway, this will be good for the first version, so let's just stop here for this time. As usual, don't forget to check out the shader files on the Nerveland Adventures repository if you want to dig deeper into this. And if you have any questions, don't hesitate to leave a comment below. Also, if you found this content helpful or interesting, please leave the video a like. And either way, I hope to see you in the next one. Bye bye!